Math 1314, Tyler Junior College, section 4.3, properties of logarithms, the power rule. At the end of the previous video, I said, well, I'll just give you the power rule. I can't remember if I said whether or not we're going to prove it, but as you can tell, we're gonna. And again, these videos about proving some of these rules are intended to benefit those students who plan on progressing beyond college algebra. The power rule says what to do when your logarithm has a coefficient. If you have a logarithm with a coefficient, the power rule says you can simply bring the coefficient in and put it as a power on the argument. Standard conditions apply. Base is greater than 0 but not equal to 1. Argument is greater than 0. There's no restrictions on the exponent though, on the end. So how can we prove this? Well, you know what? I challenge you to pause the video and try to prove it yourself. This is the third example of how to prove two things are equal by sticking both of them into a one-to-one function and showing that the outputs are the same, then draw the conclusion that the inputs are the same. So I challenge you to pause the video to see if you can take this expression, put it into this function, simplify it as much as you can, and do the same thing with this expression, which will be much easier, because immediately upon inserting this expression into the function, you get this fourth property, and then boom, that part's over. So I invite you to pause the video and try it, but I'm about to prove it, so if you're going to pause the video, now's your last chance. All right, so let's see what happens when we substitute the left side of this property into this function. Let f of x equal b to the x power, of course b greater than 0 but not equal to 1. Then f of the left side n times log base b of m. This function says give me something and I'll stick it on the b as an exponent. Okay, stick all that in the exponent. B to the n times log base b of m power. And now in order to simplify this, this is where you would analyze the structure of this expression and see if we have a previously existing rule that allows us to manipulate it. This structure has a base with a product, a base with a power, but the power is a product. So this makes me wonder, I need an exponent rule that says we get to multiply exponents, and we had one. That's when we had consecutive powers. So I can rewrite this expression as one power in parentheses followed by another power. But let's think about the most advantageous way to do this. In the previous two proofs, at some point we took advantage of this property that allowed a whole lot of things to just fall out and leave us with something pretty simple. I think it's fairly obvious that this second factor is the one that we want to isolate on this base. In other words, if the n wasn't there, then these guys would straight up cancel. So when I'm working this exponent rule in reverse, I'd like this one to be on the b. Now I know it's listed second, and in this rule it says the first exponent goes here, or the first factor goes here, but multiplication is commutative, meaning that the order in which we multiply is irrelevant. In other words, if I say x times y, that's the same as y times x. So if we disassemble this back into a power raised to another power, it's really quite arbitrary which power we put inside the parentheses. So I'm going to choose to put the second factor as the power inside the parentheses, specifically so I can take advantage of this property. So b to the n times log base b m power, log base b of m power, is equal to b to the log base b of m, b to the log base b of m power, in parentheses, then raised to the nth power. And now I can take advantage of that property over there. The base and the log cancel, leaving an m, that's m to the n power. So there's one output. And what happens if we put the second side of the property, the power rule, into our function? Log base b of m to the n power. Sorry, a little crowded there. No reason for that. I shouldn't have prematurely closed that parentheses. The output of putting the left side in is this. The output of putting the right side in is easier. This function still says, give me something, I'll stick it on the b as a power. All right, put all that in the power. B to the log base b of m to the nth power, excuse me. And right away, we have the setup for that fourth property over there where the base and the log cancel, leaving m to the n power, which is the same output. Since f of x is 1 to 1, I'm leaving some of the words out here, but since the function is 1 to 1 and these inputs produced equal outputs, then we can conclude that the inputs are equal. That's what it means to be 1 to 1 as a function. So n times log base b of m is equal to log base b of m to the nth power, which I'm going to migrate up here to the power field. N times log base b of m equals log base b of m to the nth power. Let's put a box around these. They're going to hang around here for a while. I know those of you who are not taking math classes beyond college algebra are probably a little tired of me doing all the stuff for people who are. But keep in mind that if you're taking a college algebra class and it's your terminal math class, the last one you need to take, the person sitting next to you may be at the beginning of their math journey, and as professors, we can't water things down to make it easier for those of you at the end of your path at the expense of the students who are just at the beginning. So sometimes you have to weather a little more advanced things than necessary. Whether or not you plan on taking calculus, you are on that path. Your path may just end sooner than your neighbors. But don't worry. In the remaining videos in this series, for the most part, it's just going to be pure college algebra. Not that we haven't done anything that isn't college algebra. It's just a little bit more than you would see in the standard college algebra class. All right, the next video we'll actually get down to what does my homework look like?